Yeah. Okay. So now we have seen all the types of various problems in counting regarding permutation, combination, and lots of other complicated examples involving basic principles to further extensions and conversion of one domain to another domain. Now, what last one thing remains is circular permutation. Now, what is this? Is that coming back to the old and very famous and trivial question, suppose there are 5 things which are to be arranged. So, and all the 5 things are distinct, then we will say that they can be arranged in 5 factorial number of ways. So, suppose let's say there is 4 things to be arranged, A, B, C, D. We know that they can be arranged in 4 factorial or 24 number of ways. But this is the linear arrangement, that is, they are arranged in a line. Now, what happens? Does the question change if I arrange them on a circle? Let's say I put A, B, C and D in this fashion, in a circular fashion. So will my answer of 4 factorial change? Now it turns out that yes, it will change. Answer is not 4 factorial. This answer is perhaps incorrect. So what can be the reason and why is this answer incorrect? So let us try to find out the reason and let us see what the answer is. Now if I want to arrange A, B, C, D on a circular or on a ring pattern, then it turns out that there are lesser options available. And why is it so? So consider the circular arrangement like this: A, B, C and D. Now let's say I fix A here. I fix up A. Now if I fix A here, now B, this position has 3 options, either of B, C and D, and which is left of A. This position has 2 options. Once one option comes here, this will have 2 options, which is to the right of A, and this position has 1 option, which will be left, which is opposite of A. So it will have 3 factorial ways. If I fix A as first. Now when I fix B, I fix here B, I fix here as B. Then similarly here B will have 3 factorial ways. Similarly I fix C here and I fix here D. So all of this has 3 factorial number of ways, such that if I fix one thing, the other 3 things can be arranged in 3 factorial ways. This is quite clear. This was even true in linear thing. Because once I fix this, then this will have, let's say here B, B, A, and let's say here B, A, C, D. Okay. Then so these are all the possible arrangement. But so in the linear case, it would happen that the first position can be occupied by any A, B, C and D, and each of these was 3 factorial, so we multiplied by 4 and we got the answer as 4 factorial in the linear arrangement. But now let us turn back our attention to this circular permutation. Now what the problem is here really? Now when I fix A, I can arrange B, C and D based on the direction, that is, it is to the left of A, right of A or opposite of A. There are 3 factorial number of ways. And when I fix B, again there will be 3 factorial ways. But what important thing is to be realized is that if I carefully look, this and this arrangement are identical. These both arrangements are identical. And why is it so? Because if we see here, what is there to the B's right? It is A. What is there to the A's right? B. What is there to the B's right? C. What is there to the C's right? B. What is opposite of B? D. What is opposite of A? C. So if we see, these both are same in all the terms. If we expand this from here and write down in linear way, we get A, B, C, B. I am expanding it from here and doing it binding in this way. If I expanding it from here and going all the way, I get B, A, B, C. So it is just that if I put this here, I get some another. So these two were 2 different things in the linear combination, in the normal string combination. But it turns out that these both are turning out to be same when we consider the circular thing. Yes, isn't it? Because this both ABCB and BABC when arranged on a circle are both exactly the same. And why is it so? Because this is simply a circular shift of this. This is just a right shift, or if I put the least little bit here, that is, I'm just shifting this bit from here to here, remaining all the things are same. then I get a circular shape. Now, isn't this two arrangements same? Now we can imagine a situation where there are, let's say, 4 persons or there are 6 persons on a round table. And imagine it's a round table conference. Okay, so the 6th person, if it comes to the first person, before the first person, that is, imagine this way. You need to imagine this a lot in order to understand it. So if I remove this person, okay, if I remove this person and bring him here, remove this and bring him here, this here, here, and I remove this and bring him here. That is shift everyone. That is originally it was A, B, C, D, E, F. I am converting it into F, A, B, C, D, E. Now observe that these both arrangements are identical with respect to who are the neighbors of each of the elements. Now how do we, in linear thing, what do we see? Why do we consider that these two things are different things? These two arrangements are different things because here the neighbor of B A is different. Here it is B and here it is C. Neighbor of B is well is different. It is right neighbor is C. Here there is no right neighbor at all. So similarly, but in case of circular, these two arrangements are same because here we see the neighbor of A are B and F, which is true over here as well. The neighbor of B is C and A, which is true as here as well. The neighbor of F is E and A, which is true as well here as well. So it is not changing with respect to neighbor as neighbor is concerned. So I say that these two arrangements are exactly one and the same. They are perhaps identical arrangement in circular thing. So are you understanding? This is the difference between the arrangement in linear thing or an arrangement in a circular thing. So now, if I carefully observe these two things, A, B, C, D, and here A, B, C, D, I will observe that these two things are also as well as symmetrical. Okay. So, because of this symmetricity, whom I fix first is not important because only we have to see the relative positions, isn't it? We only have to see if I fix this, what are the relative position of these three. I don't have to consider the number of choices in fixing this because it could have been that okay, I could have fixed this. Then also all the possible cases will get covered out. So it turns out that the number of circular permutations are n minus 1 times n minus 1 factorial. The number of the circular permutations are, instead of n, it is n minus 1 factorial. Why so? Because if I fix this 3 can be arranged in 3 factorial ways as we saw. But in the linear permutation, we used to take all the cases differently. That is, suppose if I fix A here, then this is 3 factorial. Suppose if I fix B here, then this is 3. C here, this is 3 factorial. And if I fix D here, then it is 3 factorial. But all these things are different. So we do 4 into 3 factorial as far as linear is concerned. So we get 4 factorial. But in case of circular, if I fix here A, then this is 3 factorial. If I fix here B, this is 3 factorial. If I fix here C, this is 3. If I fix here D, this is 3. But all these things are one and the same thing. You pick up either any one. We don't need to pick all the 4 because it does not matter whom we fix first. And what is the reason behind it? Is simple. I don't need to fix point A over here as the first point and as the necessary point that it will occur in the permutation. And the reason is very simple. Again, as I told, because we are looking at only the relative arrangement, only looking at the neighbors and not looking at each and everything. So that is why including this does not matter much. So what we do in case of circular permutation is that suppose if you want to arrange n objects, okay. So suppose let's say if you want to arrange n objects on a circular thing, then the number of ways in which this can be done is n minus 1 factorial. And how we think of this is that out of the n points we pick up any point and fix it. Let's say we fix it at some point, and then the remaining n minus 1 points can be arranged in n minus 1 factorial. Now this all arrangement will be distinct because the relative position of this point with respect to this point is different with if I put this point here or here or here or here or anywhere else. So that is why here it is n minus 1 factorial because we are looking at after all relative position. So what happens when you can think of this as an analogy of relativity in theory in physics. in relativity theory we fix one thing, and then based on what is its speed, we calculate the another speed by differentiating, by taking the difference of this speed minus this speed. Okay, so that is here we fix this point, and then we see how far is this point with respect to this point and in which direction. Okay, that is what we see basically. So this n minus 1 things are different things. All the arithmetic are different with respect to this, and it is n minus 1 factorial. So once if I have this n points, I fix this point. So automatically, suppose if I fix this point, then all the possible arrangement of this will also get covered, because this point might be sometimes here, sometime here, sometime here, here. We had considered all the possible cases, isn't it? Thus, the number of arrangement of circular permutation is n minus 1 factorial. This you need to keep in mind. And the number of the circular permutations are n minus 1 factorial. So let us see something, one more thing, garland or necklace. Okay, so this is the shape typically. Okay, so women like to wear all this string. Maybe there are some patterns, metals here. So imagine that there is something like this. So here there is something here and here, here and here. So it is also like a circular thing. It is also like a circular thing. What we do, if this total thing is n, but just one thing you have to understand is that total thing will be even. This and this will be bad, this and this will be bad, this and this will be bad, this and this, this and this, this and this, all the things will be bad. So here also we fix up anything, and the remaining n minus 1 things can be arranged in n minus 1 factorial number of ways. But there is one difference between this garland arrangement, garland and necklace arrangement, and the other arrangement of the circular permutation. What is the difference is this. This is a circular arrangement where n points are arranged, and this is the type of this type of thing, which is symmetric structure. You can have something like this as well. That you have something here, 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 and here. So that this and this are tabs. Okay. So this is a symmetric structure with respect to this middle axis. Circle is also symmetric with respect to all the axes, but the points will not be scattered anyhow. It means that the points will be somewhat more concentrated here, less concentrated here. So it need not necessarily be symmetric. It need not necessarily be symmetric, and moreover, in circular thing, it need not be symmetric, and it need not be identical. That is, let's say here person A is there, whereas here opposite to it is some person E, which is not identical. But here you may have some diamonds or some gems or some anything, let's say not even such precious metal, or let's say there will be some flowers in case of garland. So what happens is that this flower, suppose here there is any flower S, and here also the same flower will be there S. Actually, usually it is the case that all these flowers are the same. The last flower is some bigger flower or something like that. But imagine then too that suppose there are all different things I use. So suppose here some pink flower is used, then here also pink flower is used. If suppose there is some red flower, there will be also some red flower. So it will be symmetric in that sense also. Whereas here the circular is not symmetric in that sense. So if I want to consider that thing, what happens is that I fix 1 point, find that n minus 1 factorial. But even this is not. Here also there are extra counting. Why? Because in circular case, why we got n minus 1 factorial? Suppose if we had to arrange the 4 things, then the way in which I arrange left, I will say that this is my left and this is my right and this is my bottom. Okay, that is 2 left, or I can say it is 2 right. If I wanted to arrange 5 things, then this would be the case on a circular thing. 5 things if I had to arrange, then this is my to the left, second left, first right, second right. So we distinguish between the left and the right objects. In case of the circular permutation, we distinguish between the left and the right. But in case of the necklace, these both are same. They are identical. These both are, so there is no concept of left and right. There is no concept of left and right. These both are identical in all the sense. So if I take this way, then these both are identical in some sense. They are identical in sense of symmetricity. So we don't need to consider these two separately. Okay, they need to be considered only once. So what happens is that because of this, since we are considering them only once, we need to divide this n minus 1 factorial answer by 2. Okay. So this is the number of arrangement in case of a garland or in case of a necklace. Why is it so urgent as I explained? Because here we need to divide the answer by 2. Because this and this are symmetric case. So only this much thing you need to remember, extra thing from the so far what we have learned. Such type of examples are anyways rare, but you need to remember this. The circular permutation is this. In case if you want to arrange n objects on circle, then there is not n factorial number of ways. Perhaps it is n minus 1 factorial number of ways. And if there is some n objects has to be arranged on some garland or something like that, then the number of ways is actually n minus 1 factorial divided by 2. So this is what we need to know. Okay. And I would now conclude this chapter of counting and PNC with just this one very special case of example, that is called the number of D arrangements. So I will describe you what is the question and I will tell you directly the answer for it, because it is a bit not out of scope in this lecture to explain the proof and derive the proof. Okay, so the question is this. Suppose imagine that you have 4 letters for person A, B, C and D. Okay, and you have 4 envelopes. One is envelope for person A, envelope for person B, envelope for person C and envelope for person D. Okay, fine. So now what you do is that you put the letters into the envelopes. That is what we do. Now the question is, in how many ways first of all can you put letters into envelopes? So I can put any letter into any envelope. Let's say I'm a dumb, or I don't have eyes to see. So I pick up one letter, I put it in any envelope. So maybe this will have 4 choices, then this will have 3 choices. Because in one envelope I will put only one letter, and this will have 2 choices, and this will have 1 choice. So in total there is 4 factorial number of ways, or there are 24 number of ways. Out of this 24 ways, there is exactly one way which is correct. That is, A goes into envelope A, B goes into envelope, letter B goes in envelope B, letter C goes in envelope C, and letter D goes in envelope D. There is only one way which is correct. Now my question is, in how many ways, there are how many ways which is exactly incorrect? Means all the things go into wrong things. How many ways are there which are, in which all letters, or in which all letters go to different envelopes. All the letters, huh? So it is not 23, 24 minus 1. I am saying all the letters. So let's say that this is the letters A, B and C, D. I put letter A in envelope B, letter B in envelope C, letter C in envelope D, or let's say envelope A, and letter D in envelope D. Then this will not be counted in my counting, because see, letter D has not gone into the wrong place, perhaps it is in the right place. So I will not count this into my counting. So but perhaps if I change this goes into envelope B and this goes into, so that each letter will be into one envelope, but each has gone into wrong place. So you see, A has gone to B, B has gone to C, C has gone to D, and D has gone to A. Everything has gone into wrong position. This is one counting. Now this is correct. Or I can do something like this. Okay, A goes into C, B goes into D, C goes into A, and D goes into B. Or I can do something like this. That A goes into D, B goes into A, C goes into B, and D goes into C. Or maybe let me try something else, that this goes into C, this goes into A, this goes into D, this goes into B. Well, so this is one counting. So actually what you can do, this is a small example, actually you can even list down all the 24 things. Then, okay, let me write down this A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. This is 6. It's starting with A, and I can start with C, D. So here all these 6 will be rejected. Because what does this indicate? That I am sending A into A, B into B, C into C, and D into D. This is the perfect case actually. this indicates I'm sending A into A, B into D, C into C, D into B. But all these 6 will never come because A is always going into A. So out of this, let us find out out of 18. So you can actually do this. You can do this by listing and all such stuff. But how do we calculate in general? So it turns out rather it is not very easy to do this thing. But you can develop some logic and you can come up with one formula. The formula I will just explain you, the proof I will not explain, I will just mention the formula. You need to remember this and you can use that to solve the problem. But I can just mention you a brief about the idea. The idea is essentially this. Okay, so you first find out the total number of this. Then you find that you want nothing must go into any, all the 4 must go into wrong position. That is, all the n must go into the wrong positions. That is, none of them must go into the correct position. So that is same as saying that total number of cases minus everything goes into the right position minus one thing goes into the right position. That is, I say this A, B, C, D, only one thing is into its right position. All the others are into wrong position. So let's say here C, D, and let's say C, D, and B. So only one thing is into its right thing. I need to separate even this thing minus all the things in it. 2 things are same. So suppose had it been this B, then here 2 things are into the same thing. Minus the number of cases in which 3 things are in the same thing. So in general, if it is n, total number of cases minus the case in which everything is in its correct position minus the number of cases in which n minus 1 things are in its correct position minus the number of cases in which n minus 2 things are in its correct position and minus n minus 3 things in its correct position, and so on up till minus the number of cases in which one thing is in its correct position. But even this calculation is difficult to do. Here I don't want to waste much time. I will tell you the formula. The number of D arrangement in case of n objects is n factorial multiplied by 1 minus 1 upon 1 factorial plus 1 upon 2 factorial minus 1 upon 3 factorial plus 1 upon 4 factorial and so forth up till 1 raised to n factorial, and whatever sign follows it. So what sign will it be? It will be minus 1 raised to, see, for the 4th term, for the 4 factorial it is plus, for the 2 factorial it is plus. So if n is even, it will be plus, and if n is odd, it will be minus. So minus 1 raised to n, it got 1 by n factorial. So this is the total number of cases of an D arrangement when there are 4 objects. So you need to remember this for many type of the entrance exams. So suppose there are 4 envelopes and 4 letters, and I want to count how many D arrangement. That is, each letter goes into the wrong things. So answer will be 4 factorial, 1 minus 1 upon 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. So you can calculate this. So perhaps here you can take 4 factorial common as the LCM. This is always 0, 1 minus 1 factorial. You can actually remove this even from the formula. Now here it was 2 factorial, so I need to multiply by 3 into 4. Here it is 3 factorial, so I need to multiply by 4 and I need to add 1. So it is 12 minus 4 plus 1, which is 9 ways. So actually there are 9 number of ways in which all the 4 goes into the different positions. Okay. So these are the 9 things in which every 4 goes into different positions. So with this, we come to an end of our PNC topic, of our probability and combination topics. Now we move on to the next topic of probability. So now we start off with probability theory. So this chapter is actually an extension of the last chapter which we learned, that is of the combination PNC chapter. And again, this is very important chapter, and I will say actually that it is not actually any chapter, it is just an extension of counting. Again, this involves nothing but counting. Again, it is totally based on the 2 basic principles of addition and multiplication which we have learned so far. So it is not anything, something new, fancy stuff which you are seeing. It is just a natural extension of all the things, all those stuff which we have been seeing from past many years. Okay, so now we will look into the probability theory or probability and try to develop some concepts and solve lots of questions based on it, just like PNC, and get a hold on it. Okay. So this probability theory is actually very important thing. In some sense, it is similar like counting, but there are lots of topics, other topics which you need to understand properly. So we will be looking at many definitions. That is what is mutually exclusive, mutually exhaustive, independent, and such events. Then we will see conditional probabilities. After that, we will look at Bayes' theorem, and we will solve lots of questions based on all this stuff. Okay, so this is what we will be intending to cover, and maybe little here and there we will solve lots and lots of questions based on the various type of the question, various things. And you actually, if you know the counting theory well, if you now understood PNC well, if you have paused the videos and tried, and now if you are getting some hands and holds on PNC, then this is not very difficult. It is just a simply extension of all such things. Okay, so now let us start off with probability. So first of all, let us see what is a probability meaning. So most of you, as you must be knowing, or just guessing from the word, just a simple English meaning of probability is chances. So what is probability? Is just a chance. So we see that we are in this field of mathematics, we are studying the theory of some chances, which is not 100% going to be true. But we will say, oh look, this chance to some chance of this event getting occurred is this much. So why is this important, first of all? And after all, since it is only a theory of chances, right? Probability means what? Just a chances. So we are never going to be sure of anything. So first of all, why do we study all this thing? Why do we study probability? And why do we in fact study countings and all, PNC? So in the counting chapter, I had told you, I had mentioned its advantage. Perhaps I had told that it is used in so many places, and it has so many advantages. That is okay, that counting can have advantage because it helps us in count, which we cannot list down and everything, and we need all such countings to derive various formulas and to derive the estimates and all such stuff. But why do we need probability? After all, it is just an estimate. So, but if I say that something, that there is a chance that earthquake will occur with 99% chances, so that is a big fact to me, right? Because if I say that there is a chance of earthquake happening and the chance is 99%, that is a huge number. That means we need to take precaution. We need to run away. We need to do some, some special condition. We need to declare some type of emergency and all such stuff. So in that way, it is important. Secondly, statistically wise, every statistics will have something chances. Even if you see cricket matches, then we will say, oh look, today Sachin will hit a century in World Cup is this much, 90%. Everyone is expecting to hit him a century. So, but it is never always going to happen, right? Everyone will expect, oh look, Sachin must hit a century today. But it is never going to happen every time, right? Because after all, although he may have a great record, but his century record is that, once in a 10 matches. So we say that, look, he has played 400 matches, he has above 46, or he has more than 40 centuries, maybe currently he has 46 centuries. So, in every 10 matches he hits at least 1 century. So you may say, oh look, today he will hit a century. There is a 10% chance that he will hit a century. So we say in such type of things, this is not an example where you gain anything, although you may say, so what? This is not an advantage, right? And it does not matter to our economics or anything like that as such, whether anyone hits a century or not. But such type of things can even be related to the business things. Suppose, practical example, as we will see the distribution, which will not go today, binomial distribution, Poisson distribution, that in distribution, as far as the company standard, you find out what is the probability. That is, you find out, you carry out some experiments and you find what is the probability that the pen I am manufacturing will be defective. Then you find the probability that in a packet, many pens, 2 pens will be defective, 3 pens will be defective, and that is the chances. So by company standard, that answer or that probability must be as low as possible, so as to get a better market or so as to attract the customers with it. So, and not only this, it is used in various statistics analysis. It is used in even in physics, even the Heisenberg's uncertainty principle. After an uncertainty principle, if you are a physics student, you must be knowing that the uncertainty principle is based on some probability theory. He is saying that the probability that a mass, the probability that an element behaves as some wave, I don't know, actually I'm not a physics student, but I've heard something, I read it long time back, I don't recall, but it was some, so I know, but Heisenberg's uncertainty principle is also uncertainty, that is certain or uncertain, means what, that we are speaking of some probability, whether certain thing is certain or whether certain thing is uncertain. Means what, we are speaking of its chances, whether it is certain or uncertain. That is again we are speaking of probability. Even used in chemistry, the structure and all such stuff. Even used in physics, chemistry, in computer science, in a wide way. You know, everywhere there are some probabilistic algorithms as well. That is the algorithms which are based on the probability theory. That is which are called as approximate algorithms and all such stuff. So inside being some you undergraduate student or maybe a small child or maybe a graduate student, even being a graduate student, you might not have that much seen the use of this probability theory, but it is used every year and there by statistics and all the statistician and other various practical purposes in real life. So it is, first of all, so why I am speaking all this bhashan I am doing, because it is important so that you understand the importance of this chapter. It is not just any dummy chapter. It has got its own importance. So you need to be thorough with what its importance is, and you need to understand that it has some value with it. Okay. So let's not worry what can be its uses, but let us just enjoy our counting and our probability, just like how we entered our counting chapter. Let us enjoy this probability as well. So probability is a theory of chances. So probability means it gives us the estimate or it gives us the chances that something will occur. So what will occur? So that chances that can we say event will occur. Probability of an event is the chances that an event will occur. So what is in first of all event? So event is some kind of experiment which we are doing, and we want certain result. So there is something called as experiment. Then there is something called as sample space. Let us use first. Let me define all this thing, and then based on all this thing, I will define you a probability. Okay. So some event is essentially some kind of experiment is carried on. Event means what? I will tell, oh look, today there is an event. Event is of cricket match, World Cup. Or today is an event, today there is a marriage of this and this person. So that is an event, or that is some experiment is going on. Okay? So what can be an event? So in our example, typical example will be, oh look, I am tossing a coin. I have one coin with me, I am tossing a coin and I am looking what is the result, whether it is head or whether it is tail. Then I am rolling a die. Okay, I am playing Ludo and I am rolling a dice. Or I am playing 7 up, 7 down and I am rolling a dice. So all these are various experiments. So what is sample space is all possible outcomes. Sample space is all possible outcomes. What can I expect that the outcome can be? What can I expect that the outcome can be? For example, if I toss a coin, I will expect that my outcome is either head or it is either tail. So this is what is my sample space. If I roll a dice, I would expect that I would either get a number 1, 2, 3, 4, 5 or 6, because I cannot get anything other than that, right? So this is all the possible outcomes. Now favorable space means what? I want to calculate what I like or what I want. I am not interested in what are all the possible sample spaces or in what are the all possible outcomes, but I am rather interested in finding what is the chance that a specific thing will come, or what is the chance that a specific particular thing will occur. For example, if I toss a coin and if I say what is the probability that head will come, what is the probability that head will come? So I know that all possible things can be head and tail. Now out of these two things, what do I want? I want head to appear. So this is my favorable space, or my favorable outcome, or my favorable result. Right? So if I roll the dice, if I say what is the probability that a number is an even number? So this is my sample space, all the possible numbers which can appear. But what do I want? What do I like to appear as an output, as a result? I will like if 2, 4 and 6 appears. So this is my favorable outcome. Understood? So what is favorable outcome? Favorable outcome is the head quantity, is the number which specifies how many times the quantity which you want to calculate appears. And what is the sample space, or all possible outcomes, or the domain, you can say, is all the possible results that can appear due to the conduction of an experiment. Due to the experiment being taking place, what are all the possibilities that a particular thing can occur? So that is my sample space. Whereas what is my favorable space, or what is my favorable thing? Favorable thing is that thing which I am interested to find, and I find the chance that a particular thing will occur. So that is my favorable space, and this is my sample space. So all this is looking boring, but now we will come back to some question and we will enjoy it. So first let me formally define what is a probability. So probability of an event A is equal to number of points in sample space divided by number of points in, so sample space means all the possible space divided by the number of points in the favorable space. Okay, so this is what is the probability. Okay, so just I will hold it.